This video shows the ChipEnet IEEE1588 clock. The test setup is two Xilinx Spartan 3 FPGA boards connected together with a 100 megabit Ethernet link. The top trace shows the sync packet received at the slave clock. The middle trace is the decoded slave clock, and the bottom trace is the decoded master clock. Right now there are no sync packets, and you can see that the slave clock is drifting with respect to the master clock. The two frequencies are not quite the same, even though the slave clock is running off of the 25 megahertz Ethernet PHY clock, and the master clock is running off of a 50 megahertz crystal clock. Now we started the sync packets. You can see the pulse at the top trace, and you can see that the slave clock has now locked. And if we get closer, we can see that the slave clock is within 150 nanoseconds or so of the master clock. The scope is triggered off of the master clock, the bottom trace, so the jitter of the slave clock is a composite jitter of all of the various uncertainties, from the master clock jitter to the PHY uncertainty to the timestamp uncertainty and everything else. Also, the entire system is asynchronous. Now you can see that the master clock takes a drastic change. It increases in frequency by about 1.5 megahertz. The sync packets are still being sent, and the slave clock has now locked again, and the accuracy, the alignment is approximately the same as before. The IEEE protocol assumes that the delay for the packets, sync packets, are the same. In a normal Ethernet network, this is not the case. There will oftentimes be packets delayed or dropped in a congested Ethernet network or a heavily loaded Ethernet network. And we can test the performance by simulating the packet delay, random packet delay of the sync packets. And the top trace is now showing that the sync packets, up to 50% of the sync packets, are being delayed by over 100 microseconds, and the slave clock remains locked, and the accuracy, alignment accuracy, is still about the same.